Okay, when we think of CNC cutting and milling operations, we don't often think of huge construction parts or parts that are longer than, 15, 20 meters or so. And yet, as construction materials and processes evolve, there is a need for higher and higher accuracies, closer tolerances. Think of a huge wind turbine blade, which could be maybe up to 100 feet long, or some of the modern carbon fiber beams used in today's bridge construction. So for parts of that size, there is either no CNC big enough, or the CNC would have to be custom made. Now, it might make sense to go to a custom made CNC solution if the volume of the parts merited the cost, but it doesn't make a lot of economic sense for low volume products, particularly if the accuracy of a really nice CNC isn't needed. So that means currently that really large parts are basically finished, that is, shaped and drilled by hand. And that's where the Megarob comes in. The Megarob is a project that involves 7 partners, as Mike mentioned, in 4 countries throughout Europe, including one of Quality Digest partners, Hexagon Manufacturing Intelligence. And the goal of Megarob is simply to build a huge, low-cost CNC with accuracies in the 400 micron range. And by huge, I mean a 100-meter CNC. That's a 300-foot-long CNC, longer than a football field, and it could be installed anywhere. It doesn't need any kind of special environment. Now, Joel Martin of Hexagon Manufacturing Intelligence explained Megarob to me at a recent Hexagon Live show in Anaheim, California.
So the project is Megarob. It was a European initiative to create as you said, a large-scale manufacturing machine built on essentially an off-the-shelf robot that's hanging from an overhead crane and being driven by a laser tracker. So obviously when you hang a robot upside down from a crane, calibrating it, getting any level of accuracy from that aspect is very, very challenging. So what we did to overcome it was we used the laser tracker to actually guide the end effector of the robot and remove everything else from the chain. So all we're really doing is looking at the end effector of the robot, do milling, drilling, deburring, grinding, polishing, painting, whatever application needs to be done for this large-scale manufacturing process. And having the tracker guide the end effector of the robot to get to the accuracies and the uncertainties that you would use in a traditional small-scale application, but for large-scale parts, 10 meters, 20 meters, 30-meter parts. The goal here is to really get, number one, to make the volumes larger and to make the cost less. So to be able to take a machine that we can do low volume manufacturing where it may be cost prohibitive to do a large scale CNC machine, a 12 meter or a 20 meter NC machine can be incredibly costly. Hanging a robot from an overhead gantry, most people have 90% of that solution already in their shop already.
Did you hear about the list of? Did you hear the list of parts that Joel gave? These are off-the-shelf parts. There's an off-the-shelf overhead crane, a GH overhead crane in this case, but a lot of people make these things. They are essentially off-the-shelf. An off-the-shelf Comau industrial robot hanging upside down from the crane. You can see it in the picture there, and a CNC head built of off-the-shelf parts, and an off-the-shelf Leica laser tracker from Hexagon Manufacturing Intelligence, and of course all the adapter plates and cables and so forth that kind of glue it all together. Now, the secret sauce in all this is the software that allows the laser tracker to control the robot. And this is where the trick comes in. You see, the accuracy of a traditional CNC lies in the actual build of the CNC, the rigidity of the CNC, as well as its error mapping software. So the accuracy is self-contained, so to speak. With the Megarob, the accuracy is based on the ability of the laser tracker, an outside element, to monitor the position of the cutting head and feed corrections back to the robot so that the head is kept on track. So concerns like temperature or the overall stiffness of the machine structure are much less of a concern. Here's how it works on a small-scale demo.
So obviously bringing a 20-meter machine here would be a little challenging, so we shrunk the demonstration down. The idea of what we're showing right now, we have an off-the-shelf robot, nothing different done to it, being tracked by the T-Mac on the end effector and the laser tracker tracking the robot. And to show the idea of instability of hanging a robot from a crane, we basically put the robot on a translation slide. The slide is moved by a human, so there's no correction or calibration to the slide. And what you're seeing is as the robot draws the shapes, so we're drawing a circle, a hexagon, and a square, and we're going to draw it once in an uncorrected format. And as I move the joystick of the robot, the slide is moving an unknown amount. So as far as the robot's concerned, it's following a trajectory path. And as you can see, the shapes are now skewed because the robot base moves, the robot program is uncorrected, so it draws a shape that isn't looking like what the shape should look like. When we rerun the program and we use the laser tracker to drive the end effector, you can see the base of the robot still moving in an unknown amount, but now the end effector of the robot is being corrected by the laser tracker in real time at 1,000 hertz, and what we end up with is shapes that are correct. So regardless of where the base of the robot is, regardless of if the robot was hanging upside down from an overhead crane with temperature variation, vibration, swaying in the wind, the end effector is doing exactly what we're telling it to do in a precision path.
Well, that was a small scale demo, and demos always work great, right? That's why they're demos. But how well does the actual machine work? Well, you heard Joel say earlier that the current Megarob, which is still in development, is about 20 meters long. So what is that, 64, 65 feet? Long enough to machine a composite part for, say, a bridge, which a company called Acciona did. It looks something like this one. This is a composite footbridge built by Acciona in Madrid. It's a typical construction of most of Acciona's composite bridges. The beams that make up the bridge are similar to a bridge piece that was just machined by the Megarob for Acciona, and we can see it here. This is a 12 meter by 1.5 meter by 2 meter composite beam built of carbon fiber, and we can watch here as it's being cut on the Megarob. If we can run that little clip. In the past, after layup, this piece would have taken about 20 hours of manual cutting and drilling with hand tools to get to the needed tolerances. With the Megarob, it only took 6 hours. So we're talking roughly 3 days on the site versus 1 day on the site to get these same accuracies. Now, as for accuracy, in the past, the finish tolerance on the contour, on the shape, was about 12 millimeters or half an inch. With the Megarob, the finish tolerance was 300 microns or about 1/100th of an inch. In the past, hole positions were within 4 millimeters, so a 1/7, 1/8 of an inch. With the Megarob, hole positions were held to within 50 microns. That's 2/1000ths of an inch. So it's way faster and way more accurate than what you traditionally have been able to see finishing parts by hand. Not to mention it's a lot safer. Now there are some caveats to the Megarob. One is accuracy. It's a few hundred microns as opposed to maybe 50 microns on a true CNC machine, if you actually had access to a CNC machine that big. And the other caveat is that currently you are limited to soft materials, no harder than, let's say, soft aluminum alloy. So really what we're talking about at this point is carbon fiber and the like. Those are the obvious materials right now. So what does this actually all mean? Well, think about it. If your tolerances are only in the few hundred micron range, then this technology means that you can do CNC finishing work almost anywhere you can find a big warehouse. So think about installing a huge CNC in a warehouse or on or near the job site. Think of the ramifications that has for construction. You know, rather than, let's say, finish parts somewhere off-site and then ship them to the site, you could have unfinished parts, beams for instance, composite beams in this case, sitting in a warehouse on site and then finish them as needed. You could literally make changes on contours, on hole positions in CAD overnight, put them onto the Megarob, and by the next morning you would have your finished part. It's an amazing project. Really what it stands to do, I think, for construction and large-scale construction is really pretty amazing, is pretty groundbreaking, I think. So that's it. That's the Megarob from
Hexagon
Metrology, one of our partners. And as I said, if you want to see more information on the Megarob, there's a link that goes out there. There's actually also some interesting videos on there as well.